Okay, so now it's time to talk a little more about what happens when the degree on the top is larger than the degree on the bottom. Okay, the other two possibilities are actually pretty easy. You have when they have the same degree over the same degree, it's just the leading coefficients. When the degree on the top is smaller and the degree on the bottom is bigger, then you have the horizontal asymptote y equals 0. So those are really pretty easy to find. But when you have a larger degree on the top than the bottom, there's quite a few things going on there. And so it deserves a little bit more talking about. So if you take a look at the first one, the f of x, you have 3x to the third with all these other things divided by x plus 2. So we're really looking at the leading terms. Okay, so only look at the leading terms. And of course, the leading term means the term with the largest degree. Usually it's listed first, but you may have to like rearrange things, right? So look at the leading terms of the numerator and the denominator. So in this case, we have 3x to the third, and we have an x. So because we're talking about end behavior, what's happening at end? So end behavior means as approaching infinity or approaching negative infinity. So the x number, the number in there is going to be really, really big. So talking about millions or billions or trillions, right? So that's why we don't really look at the rest of the function, because when you're taking a million and cubing it, or like a billion or trillion and cubing it, you're getting such a large number that the other numbers don't really affect the ends of the function. Okay, so if we are talking about this function with 3x third on the top, and on the bottom we're looking at just an x, those are the things that determine what's happening at the ends. So those are called the end behavior model. We're going to reduce that. So simplify just that function, simplified function, 3x squared, and that is called the end behavior model. Okay, so in other words, at its ends, this fancy rational function is behaving like a quadratic, and it like with a coefficient of 3. Okay, so that's really all we have to do for these is find that end behavior model there. All right, so in our second one, we're looking at 6x to the fifth on the top and 2x squared on the bottom. We're going to ignore the other terms because they won't be big when we're looking at its ends. So this would be 6x to the fifth divided by 2x squared. You will do 6 over 2 and get 3. And then when you're dividing x to the fifth divided by x squared, remember you would subtract the exponents. So 5 minus 2, 3. So our end behavior model, I like to just EBM, okay, but in the MyMathLab and everything, they call it the end behavior model, is just y equals 3x to the third. Okay, for our last one, we have a 3x to the fourth and an x to the third. Okay, so 3x to the fourth divided by x to the third. So our end behavior model is 3x. Okay, notice that the EBM is linear, and that is because the degree on the top is exactly 1 higher than the degree on the bottom. So degree on top is 1 greater than the degree on the bottom. Okay, so in this case, this is what's called our slant or oblique asymptote. And we're going to need to do a little bit more work on it. Okay, so let's look at that one just in a little more detail. In this case, they're actually not going to ask us for the end behavior model. They are going to ask us for the slant asymptote. So finding the slant or oblique asymptote. okay, we are actually just going to have to divide the numerator by the denominator. Okay, so in some cases we'll be able to use synthetic division, and that makes this problem really easy. And in other cases we're going to have to do long division because, I mean, we can't do synthetic division here, right? So we're going to have to do long division because, like, what would we put on the shelf for x cubed minus x squared plus 1, right? So we have to do long division. So I'm going to say long division or synthetic division. And in this case, we must use long. So we are doing 3x to the 4th. Remember, we're going to want to put a 0x cubed in there, minus x squared. And then we might need a 0x and a 0. I don't know if we'll need all those terms. We'll see. And on the outside, we have x cubed minus x squared. I'd probably put a 0x in and a plus 1. Okay, now remember with long division, okay, we've done this before, so I'll try to go pretty quick. You want to divide 3x to the 4th divided by x to the 3rd. So I like to write that over on the side, 3x to the 4th divided by x to the 3rd. It's just the leading term divided by the leading term. And so that would be our 3x, right? Okay, now we multiply. So 3x times x cubed is the 3x to the 4th. 3x times negative x squared is negative 3x cubed. And then 3x times 0x is 0x squared. 3x times 1 is 3x. And we won't have a number over there. All right, now we subtract. So we're going to subtract, remember, we're going to subtract all these second terms. Okay, so that one, of course, is 0. This one is 0 minus a negative 3, so positive 3x cubed. This is just 0. So I'll just write it just in case though, right? So plus 0x squared, I might need it next time. And then this is 0x minus 3, so that's minus 3x. And then I could still bring down that 0 in case I need it later. All right, next term, okay? So now I start over. Remember, I just repeat the process. So now I have 3x cubed divided by x cubed. So this one is 3x cubed divided by x cubed. Oh, well, there we go. That is 3. So plus 3. It's a positive 3 there. All right, now I multiply. So 3x or 3 times x cubed is 3x cubed. 3 times negative x squared is negative 3 x squared. 3 times 0 x is 0x. And 3 times 1 is 3. Oh, see, I did need that 0. I'm happy I wrote it. I was just having faith there. All right, now subtract. Nothing there. This will be positive 3x squared. This is minus 3x, and this is minus 3. Don't panic. I know this is like, oh my God, it's so much work, but you're actually done, right? Because this is the remainder. Our quotient is 3x plus 3. We can't go lower than just a constant term, right? And look, if we try to divide 3x squared divided by x cubed, no, right? That's not going to give us a number that we can put up here. So this is the remainder. And guess what? We don't need it. Okay? So our slant or oblique asymptote, let's call it the slant asymptote, is the line y equals 3x plus 3 from right here. Okay, so First of all, notice that we actually knew the 3x already from our end behavior model. So really all we were looking for was the constant term, because now we could actually graph that line if we needed to, right? 3x plus 3. And second thing to notice is you don't need the remainder. And that's because if you did use the remainder, you would actually just be talking about the original function, wouldn't you? Right? 3x to the fourth minus x squared divided by this thing is literally 3x plus 3 plus this remainder. So when we leave off the remainder, that's when we're talking about the slant asymptote, because it's the number, it's the line that the graph approaches. It's not the graph itself, it's the line that the graph approaches. Okay. In the next video, we'll do another oblique asymptote, but one that we can actually use synthetic division for.